Electromagnetic induction. Faraday's law of induction states that when there is a rate of change of magnetic flux or change of magnetic field in a conductor, an EMF is induced in the conductor, which opposes the change making it. Lenz's law states that the direction of the induced current flows to oppose the change making it. When there is changing magnetic field in a conductor, if this is an open circuit, there is only induced EMF, but not induced current. If the circuit is a closed circuit, then both induced EMF and induced currents are present. Case 1. Consider stationary conductor in a changing magnetic field. If a bar magnet is pushed towards a solenoid, in this case, the north pole of the bar magnet is moving towards the solenoid. Hence, there will be a change of magnetic field in the solenoid. By Lenz's law, the NP near the solenoid will be induced north pole. Hence, there is induced current flow in the direction shown. Hence, the needle of the galvanometer will deflect to the left. However, when the bar magnet is now moved away from the solenoid, that is, the south pole of the bar magnet is moving away from the solenoid, hence, there is still changing magnetic field in the solenoid. By Lenz's law, the NQ near the solenoid will be induced north pole, hence, there will be induced currents shown in the solenoid. As a result, the needle of the galvanometer will deflect to the right. Consider the case a bar magnet is rotating about an axis passing through O and perpendicular to the plane as shown in the diagram. The north pole is moving towards the solenoid. There is a change of magnetic field inside the solenoid. Hence, by Lenz's law, there will be an induced current flows to oppose the change making it. Therefore, the NP will be induced north pole. Hence, the induced current flow in the direction shown. In this case, the galvanometer needle will deflect to the left. Later, the north pole is moving away from the solenoid. In this case, there is still changing magnetic field inside the solenoid. Therefore, by Lenz's law, the induced current flows in a direction to oppose the change. Hence, the NP will be induced south pole, and the induced current will change directions. Hence, the galvanometer needle will be deflect to the right. In this case, we can have alternating current. To increase the induced current, we can use stronger magnet. Rotate the magnet faster and increase number of turns of the solenoid. Consider a small bar magnet falls freely into a metal ring. When it is falling down towards the metal ring, the metal ring will be induced a pole, north pole, on the upper end. Hence, the induced current flow in the direction shown. When the magnet is inside the ring, there is no change of magnetic field in the ring. Therefore, there will be no induced current. After the magnet passes through the ring and still falling down, the lower end of the ring will be induced north pole to oppose the change of magnetic field making it. Hence, the induced current will flow in the direction shown. Next, consider a moving conductor in a uniform magnetic field. By using Fleming's right-hand rule, we have the thumb represent the motion. The first finger represents magnetic field. The second finger represents the induced current. If the conducting wire is moving along the z-axis, or we say is moving upward, by Fleming's right-hand rule, the induced current will flow in the direction shown. Hence, the galvanometer needle will deflect to the left. If the conducting wire is moving downwards or towards the negative z-axis, an induced current will flow along the conducting wire in the direction shown. Therefore, the needle of the galvanometer will deflect to the right. However, if the conducting wire is moving along the y-axis, in this case, the motion and the magnetic fields are parallel. Hence, there will be no induced current. Similarly, if the conducting wire is moving along the x-axis, there will be also no induced current produced along the wire. An AC generators make use of slip rings and carbon brushes. If the coil rotates clockwise, when the plane of the coil is parallel to the magnetic field as shown in case 1, the induced current will flow in the direction shown. Hence, the needle deflects to the left. After a quarter of period, the plane of the coil is perpendicular to the magnetic field. In this case, the direction of motion of P and X is parallel to the magnetic field. Hence, there is no induced current. Therefore, the needle remains at 0. At half a period's time, the plane of the coil again parallel to the magnetic field. In this case, the induced currents at X and P are in the direction shown. In this case, the needle of the galvanometer will deflect to the right. At time equal to 3/4 of a period, the plane of the coil is again perpendicular to the magnetic field. Hence, there is again no induced current. The variation of induced current with time will be like this one. Notice that when the plane of the coil is parallel to the magnetic field, the induced current has greatest magnitude. However, when the plane of the coil is perpendicular to the magnetic field, there will be no induced current. To make a DC generator, the only change is that we replace the slip rings by commutators. Similar to AC generator, at t equal to 0 and t equal to half period, the induced current has greatest magnitude, with direction shown through P and X. However, the needle deflects in the same direction, that is, deflects to the left. At t equal to a quarter period and 3/4 of a period, the plane of coil is perpendicular to the magnetic field, hence there will be no induced current. And the IT graph will be like this one. We call DC. Magnetic flux. Consider a coil rotating in a uniform magnetic field as shown in the diagram. Magnetic flux phi is defined as NBA cosine theta, where N is number of turns in the coil, B is the magnetic field strength, A is the area of the coil, theta is the angle between the axis perpendicular to the plane and the magnetic field. When the plane of the coil is parallel to the magnetic field, magnetic flux phi equal to 0. When the plane of the coil is perpendicular to magnetic field, magnetic flux phi equal to NBA. Notice that unit of magnetic flux is Tesla meter square or Weber. Induced EMF in a coil rotating in a uniform magnetic field. When the coil is rotating with an angular speed omega, by definition, the induced EMF magnitude is equal to N d flux dt, which is equal to N omega BA sine omega t, equal to 2 pi f NBA sine omega t, where f is the frequency of rotation of the coil. 2 pi f NBA is equal to the peak voltage of the induced EMF. If at time equal to 0, theta is 0, half of induced voltage against time t will be a sine curve with peak voltage E0. In order to increase the induced voltage, we can use greater turns of coil, use greater magnetic field, or increase the area of the coil. Lastly, we can increase the frequency of rotation of the coil. Magnetic flux density, B, is defined as the magnetic flux per unit area, that is, B equal to flux over area, provided that the magnetic field is perpendicular to the coil. Notice that magnetic flux density is identical to magnetic field strength with unit of Tesla or Weber per meter square.